Professor Andrew Newsam is one of those rare individuals who manages to explain complex science in a way the rest of us can understand and wonder at. He studied cosmology at Glasgow University and worked as an observational astronomer at the University of Southampton before joining LJMU in 1998 as an education and research fellow with the Astrophysics Research Institute, renowned for the Liverpool Telescope, notably the world's largest fully robotic telescope. He progressed into lecturing in 2005 and became the director of the National Schools Observatory. In 2012, he became a professor of astronomy, education and engagement. And he is also the author of the book, Everything You Ever Wanted to Know About the Universe and Our Place Within It. This book has been described as a brilliantly vivid guide to the incredible mysteries of space and to ourselves. As well as his work in astronomical research and education, he is an active and passionate science communicator, giving talks to many thousands of school children. And he believes, if you can explain the universe to kids, you should be able to get some of that information through to less receptive adults. Let's see how we do. Ladies and gentlemen, Professor Andrew Newsam.
Thank you. Good afternoon. Thank you all very much for coming along. It's a real honour to be standing up here. I've been excited by the Roscoe lectures for a long time now, and to actually be giving one myself is quite a treat. I'm going to be talking this afternoon not just about space, in fact, not very much about space, but why space and understanding space is important to us. And I'm going to be doing that because in my time developing as an astronomer, working at this university, I've come to realize that if all you ever do is think about your day-to-day job, if all you ever do is think about the questions you're trying to answer, you're missing out on some of the most important and exciting aspects of the work that we do. So just to give a brief outline of what I'm going to talk about, we've got this here. I'm going to start with a bit of actual astrophysics. That's the small bit. What I'm really going to be talking about is how that fits into the wider world, in particular how it relates to our understanding of science and technology and engineering and maths, how we share that with other people, so public engagement, my own journey through public engagement, which has been quite a weird one, and then I'll get on to what I consider to be the meat of what I want to talk about this evening, which is astronomy education, and from that, the National Schools Observatory. But I will start with the astrophysics. Here at John Moores University, we have a department called the Astrophysics Research Institute. And in that department, we do research into quite a large fraction of the universe, trying to understand what's going on, trying to see what it tells us about the fundamental nature, not just of the universe, but of ourselves, and the atoms we're made of, and the forces that hold us together. And so we cover everything from galaxy formation and evolution, looking at the largest structures in our universe, how they form, what's going to happen to them in the future, where they come from in the first place. We study that by looking at them, big telescopes, taking nice pictures, taking measurements, trying to understand what's going on. But we also do it inside computers. This is a very important aspect of all modern science, but I think particularly science like astronomy. Instead of looking at something and trying to understand it, you look at it and then you try and build a computer model of everything that's going on in that galaxy. And then you don't just look at it, but you see how it changes. You can see how a galaxy is formed. You can see how it changes over billions and billions of years, what it might do in the future. And you compare that with what you actually see, and if it's different, then there's something wrong with your computer model. And that's a great thing. Because if there's something wrong with your computer model, it means you can improve it. And if you can improve it, then you've learned something new about the universe. So we do that sort of work by looking at entire galaxies, or even entire parts of the universe. But we also do that to look at stars, individual stars like the sun, To us, it's just a big glowing ball in the sky. It's what makes it warm on a sunny day. The absence makes it dark at night. But what's going on inside that is absolutely fascinating. There's very complicated nuclear reactions going on that are creating new elements, new kinds of particle. And they gradually make their way out to the surface, and then that heat comes out and it glows and provides all the heat and energy we need upon the Earth. So understanding how that happens, where stars come from, where they're going to go to in the future, what's going to happen to the sun? Is it still going to be there when we need it to be? Short answer, yes. We've got about 5 billion years before the sun disappears, so nobody needs to panic. But understanding that, looking at stars, working out what's going to happen to them in the future, allows us not just to understand stars, but understand where the very elements that make us come from. Most of the different atoms in your body were made inside stars. We understand that, but we don't really understand how they get to us, because if they're stuck inside a star, they're no good to us. We have to wait for those stars to explode and the material to be thrown out into the universe and eventually stick together, form a planet, form us. So these are really important questions to try and understand. Where do these atoms come from? How do they end up in us? Until we understand that, we don't know where we came from. So this is not just esoteric looking at dots in the sky and trying to work out why they're that color, but really understanding the fundamentals of ourselves and our future. But then we get to the other stuff. This is the sort of area that I tend to be personally involved in, things like time domain astrophysics. Time domain astrophysics basically is stuff going bang. We like things that go bang in the universe. They're fun, they're exciting, but they're also extreme. And anything extreme tells you more about what it's made of. You can look at something, let's say you can look at a car. The car goes forward, the car goes backwards. Everything's fine, but you don't understand how the car works until you take it to pieces. And the way we take things to pieces in the universe is we look at them until they blow up. That seems to work quite well. And so time domain astrophysics is trying to find these things as they're exploding and understand what's going on. And to do that, you have to be able to see them in detail. And that involves building telescopes and instruments, cameras to go on those telescopes. And we're unusual in that we have our own part of the department that does that. They design and build telescopes and instruments. So working together with those who are doing the research into the universe to design the instruments that we need to understand what's going on. That's quite unusual. That's quite innovative. That's something that JMU has led the way in a lot in astronomy. So that's something that we're particularly proud of. And in the bottom right-hand corner, I have some rhino. I suspect at least 2/3 of you have been sitting there thinking, why has he got a picture of rhino? This is an offshoot that came about because of a conversation over a garden fence, quite literally. One of my colleagues, Steve Longmore, was out in his back garden, and his next door neighbour, Serge Wieck, got chatting to him. Now, Serge is an ecologist. And Serge was explaining some of the problems that he had with his work to Steve, in particular, monitoring populations of animals in the wild. Because that's really hard, because they hide, and they cover very large areas. You've got an entire rainforest to look at. And it's very difficult to know how many they are, where they are, what state of health they're in. But Steve is an expert in infrared astronomy. And so between them, they came up with the idea of taking infrared cameras, putting them on drones, and flying them over the forests. And then automatically taking the videos from those infrared cameras, putting them through this kind of software that Steve uses to do his astronomy to automatically find different kinds of animals and count them. And that's turned into a large project where they're doing a huge amount of work to help with the conservation of rare species all over the world. And it's even growing to do things like helping with air-sea rescue attempts and finding underground fires in peat areas of Indonesia. So this is an offshoot, but it's become an important one. And I think that's the first hint of what I really want to get to this evening, the way that astronomy can broaden itself and help other areas of science and technology. Now, the department itself is in this building, up near the Catholic Cathedral. Some of you may recognize it. It's been around since 1992. I joined about 6 years later. It started off with about 1.5 people, one of whom's here. And it's now over 100 people, so it's become a very large department. This is one of the largest astronomy departments in the country. And obviously, it includes research. It's the Astrophysics Research Institute. But there are actually 4 equal strands to what we do. There's the research, there's teaching. We have undergraduate students, we have postgraduate students. We work with them because they're the next generation coming through. We have the technology that I've already mentioned, the instrument development. But we also have education and engagement, and that's my bit. That's the bit that really gets me excited and drawn into it. And for the rest of this evening, I'm not going to talk about astronomy and space. I'm going to talk about education and engagement and why I think it's important. And I think it's important because of things like this. These are things happening in the world now that we need to be very concerned about. We've just had a pandemic. That picture on the top right, by the way, top left, is the coronavirus. That's what's been causing all the problems. It's a little smaller than that, but it's very nasty. We have a global financial system, which, frankly, I don't think anybody actually understands. And one of the reasons it's hard to understand is it's not necessarily entirely driven by people. Computers are starting to make a lot of the decisions that go along in there. We've got artificial intelligence. Many of you will have seen the headlines recently about this new ChatGPT system and the problems that's likely to cause, but the potential it has to be so exciting. So artificial intelligence is something that's going to radically change all of our lives. And then we have global warming, climate change. That is the biggest single problem facing the Earth, no questions. And one thing that all of these have in common is that they have a very strong relationship with science and technology. In some cases, science is creating the problem, but in all cases, science could help to provide the solution. So if you want to be able to connect with the world around you, if you want to be able to look at these challenges and be confident that we can find solutions, an understanding of science, not the details, but the nature of science, is incredibly important. Now, at the moment, most people in the world trust scientists. That trust has actually grown slightly during the pandemic. And I think that's a positive thing. I would think that. I'm a scientist. I like to be trusted. But I think that is a positive thing because if we can't trust scientists, then it will be very hard for them to come up with the solutions that we need. But another statistic, which is more worrying, is that 57% of people around the world think they don't know much or anything about science. And I think those two numbers are a problem, because I don't think that uncritical trust is a good thing. It's very nice to be trusted as a scientist, but I'd far rather be trusted by somebody who understands what I'm doing. So I think we need to do something about this. We need to get those other 43% of people and get them to appreciate what science is. To a lot of people, science is just this big black box, and you put numbers in one side and you get knowledge out of the other. And that's not what science is. All science is a very sophisticated technique for answering questions. That's all it is there to do. The answers themselves are not really science anymore. It's the process of finding those answers. And that means that although it's a very powerful technique, there are some things science cannot do. Maybe science will never be able to answer these questions. Maybe it'll just take some time, but there are lots of very important questions that science currently cannot answer. And that limitation is as important as the things that science can do. Understanding what science is able to do, what it can't do, what it's good at, what it's bad at, an understanding of that will help people to connect better with the world around them. And this is becoming an increasing problem, because although most people trust scientists, there are some who don't, and they can be quite loud. Conspiracy theorists, extremist ideologists quite often have an anti-scientific aspect to them, treating scientists as part of some giant global conspiracy. I'd love to be part of a giant global conspiracy. Unfortunately, I haven't had the opportunity yet. So there is a challenge here of breaking down these worries that people have, because a lot of this anti-scientific stuff comes from a genuine and understandable fear. If these people out there who call themselves scientists are changing the world around you radically, and you don't understand what you're doing, that can be terrifying. And one very natural reaction to that is to kick against it, to assume that the scientists and the science is against you rather than for you. And I think we need to do something about that. And one of the problems that we're facing with that is there are fewer and fewer people available to actually do the science and to do the technology and engineering and mathematics that we need in order to be able to solve these problems. Globally, there is a shortage of people with the right skills. And we need more in the future, and there's going to be fewer. And that's a very big problem, and it's going to get worse. And some aspects of that are very visible. These two pictures are of two graduating classes from two different universities. One of them is a class of computer scientists. The other is a class of nurses. I don't have to tell you which one's which, because there's a massive and significant lack of diversity across most professions, not just the scientific professions, but in the arts, in studies of English literature, in law. A lot of these professions have a very poor diversity, often gender diversity, also things like social background and ethnic diversity. And that's obviously bad because it means that you're not getting enough people to do some of these professions. But it's also bad because it means a very large number of people are growing up and joining a profession which is second best for them. They're not doing the subject that they should be doing. And they're not doing it not because they aren't capable, but because prejudices and biases and stereotypes that they picked up when they were young have stayed with them, and they just assume they can't. And breaking down that barrier alone, if everybody who left school and went to university chose the subject that was the best for them personally, quite a lot of our problems would very rapidly disappear. Which brings me to the idea of public engagement. Public engagement, in my view, so this is public engagement with science and technology, that's about helping people to critically connect with the technology and scientific world around them. It's not about teaching people things. You can teach people things as part of it, but it's breaking down the barriers, breaking down the fear, breaking down the lack of understanding, but in a way that isn't entirely, isn't science wonderful, go away and be happy. It's about allowing people to understand where the science can help them, where it can't, and where they should be skeptical, where they should be suspicious. That critical appreciation of science and technology is very important. And so sharing what we do, the science and technology that we're surrounded by and that we help to develop, sharing that with people is a very important part of the modern scientific world. And I think astronomy has a particularly important role in this because it's popular. People like space. In this country, there's something like 400 or 500 amateur astronomy societies. There is not a single amateur particle physics society. I don't know why not. To me, they're both equally interesting branches of science, but for some reason, astronomy catches people's imagination. And it's not controversial. I mean, there are small controversies within astronomy, but there aren't very large ethical issues. It's not political. I mean, the funding of it might be political, but the things we discover are very rarely political. And it addresses big questions. Where do we come from? Where are we going to? Are we alone in the universe? These are questions people want the answers to. They're interested in. And of course, we make nice pictures. And never underestimate the power of a pretty picture. I did a sort of impromptu survey of some of my colleagues at a conference a few years ago, and I just asked them, what got you interested in science? What got you interested in astronomy? And a large fraction said, I saw a nice picture and wanted to know what it was. And so being able to create these images, these observations of things out in the universe, which connect with people's aesthetics as well as their knowledge, is an important part of the engagement. And because I've become increasingly interested and passionate about this, this has started to change my career. I thought it'd be worthwhile giving you a quick rundown of how I ended up here, because some of you are probably wondering. I started out with a very normal route into academia. I did a degree in physics. Actually, technically, it was a degree in physics with computing, but nowadays we call that physics. It's now the same thing. And when I'd finished that, I was quite enjoying it. I was very academically minded, so I went on to do a PhD. I did my PhD in astronomy, in cosmology, at Glasgow University. This is me at my graduation ceremony. I've changed a bit. And after that, I went down to Southampton, again following the standard route into academia. You do your first degree, you do your PhD, and then you have what is known as a postdoctoral job, which is usually 3 or 4 years. You might do a couple of those, and then if you're lucky, you end up getting a lectureship at a university, and you're set up for life. Honestly, it's not quite that smooth, but in principle, you're set up for life. And I was quite happy to go through that route. I had my first postdoctoral job. There was another one lined up for me to continue. Everything was looking smooth. And then I saw this advert for a job at Liverpool John Moores University. And it wasn't a postdoc, and it wasn't a lecturer. It was a mixture of things. Some of it was research, but some of it was working with schools and working with the public. And 25 years ago, that was not a thing. Nobody did this. The only scientist anybody had heard of was Heinz Wolff. That was it. Communicating with the public was just something that wasn't done. And suddenly here was a university that said, no, we need to do this, and it's important enough to actually pay somebody to do it as part of their job, not just stuck on the side, but as a core part of their job. That was incredibly forward-looking. This is now everywhere. Most science departments in most universities in this country will have somebody whose job it is to do this. But I was lucky. I was one of the first. I got offered this job. I couldn't resist it. And so I took the job, and I came up to Liverpool, and I've been here ever since. And that's me sitting in front of the computer I had then. And that started me on the path to sharing what I find exciting and fascinating about science with as many people as possible. And to do that, you've got to find ways of reaching them. And so I spent a lot of time doing weird stuff. The map on the left there is one of my tours. I spent a year and a half touring around schools all over the country. And this is my GPS track. I don't drive, so I did the entire thing by train. So that's a pretty good map of the UK train network. I've worked with street theatre people, the science butlers. I've worked with sculptors. Andrew Small produced this wonderful sculpture. I do lectures for schools and colleges. And I've worked with dance companies. IJAD Dance do some fascinating work with training up young dancers to understand how their bodies work better. And I was able to work with them and explore the nature of gravity with them, which was very interesting. Bizarrely, and I still don't know quite how this happened, I had my own exhibition at Tate Liverpool. That was fun. Still don't know quite why, but it was very interesting. I've helped to develop show gardens. We had a show garden at the Chelsea Flower Show, an award-winning show garden based around the concept of dark matter, which may not even exist. So that was another exciting one. My personal favourite, I've been on Blue Peter. I loved that. And yes, I have a Blue Peter badge. And yes, it's one of my favourite possessions. That was an amazing week, getting the filming of that. And I've been involved with theatre companies like Unlimited Theatre, who produce plays for children. So I've been able to work with lots of other people who have their own way of connecting with audiences. And I've been able to bring the science into it. But that, again, isn't really what I want to talk about. What I really want to talk about is how we use astronomy in education. Because I've already said one of the challenges we have is that as people grow up, they develop these prejudices, they develop these biases as to what they can and can't do, what a scientist looks like, what an artist looks like. And if it doesn't look like them, they disconnect. And if you want to change that, there's no point waiting until they've left school. You've got to get them young. You've got to get them before they develop those prejudices, before they develop those stereotypes. And again, astronomy can be a very powerful tool to do that, because we have the evidence that school children retain their interest in astronomy even when they're losing their interest in other parts of science. There was a bit of research done back in 2000, but it still holds, which was looking at the views that pupils had throughout primary and secondary school of all the subjects that they studied. And one of their conclusions was that the one topic in the sciences that generated universal enthusiasm was any study of astronomy. Every other branch of science, as they get older, kids get less and less interested, but not astronomy. And that doesn't matter on their age, their gender, their social background, their ethnic background. This holds true. And that's wonderful for astronomy, but it's also a responsibility. We need to use that. We need to take that and make sure that we use that to help these children grow up with fewer prejudices, with fewer stereotypical views of what they can and can't do. And in JMU, we have a unique way of doing this because we have this. This is our beautiful toy. This is the Liverpool Telescope. As you've heard, it's the world's largest fully robotic telescope. It's on La Palma in the Canary Islands, which is a beautiful island. It's not as touristy as some of the others because it doesn't have the beaches. But if you're visiting the observatory, you land out down at sea level, you get in the taxi and you start winding up the mountain, and you go past the pineapple groves and the banana plantations and so on, typical of any tropical island. You wind up the mountain, and then it starts to get misty. Then it gets foggy, and everything disappears. And then suddenly, you break through the top of the fog, and you've come out above the cloud layer. And spread in front of you is the top of this mountain. And right at the peak are some little white dots, which are the domes of telescopes. And inside one of them is this. This telescope is owned and operated by JMU. It's been running for about 15, 20 years now, doing very exciting science. Not because it's actually particularly big, it's one of the smaller telescopes on the island, but because of that important phrase, fully robotic. It's not how big it is, it's how it works. Now, normally, if I want to use a big telescope, I have to travel to wherever the telescope is. So I spend a lot of my time traveling to places like the Canary Islands and Hawaii and Australia. It's a really stressful job. And you travel to these places and you go to the top of the mountain and you spend your 3 or 4 nights gathering data, and then you bring it back and you do science with it. And that's fine if what you're looking at is sitting there waiting for you. So if I'm studying galaxies, which don't change for millions of years, this is fine. But if I want to look at a star that's exploding, this isn't going to work, because when I get there, the chances of one exploding at the right time is pretty small. So I don't want to have to go to where the telescope is. I want the telescope to be able to make decisions for me. I want it to be able to suddenly start observing a star when it finds one that is exploding. And so that's why this telescope is operated differently. Instead of sending astronomers to the telescope, we ask them to tell us what they want it to do. We call them observing programs. And that describes what they want the telescope to do for them. It might be look at the same star every night for a year, or it might be wait for a star to explode and then immediately start observing it. We then take all of those requests from dozens, hundreds of astronomers, and we send them out to La Palma over the internet, wonderful thing, and we go to bed. Actually, no, let's be honest, we go to the pub, then we go to bed. But while we're busy drinking or sleeping or whatever we're doing, the telescope is doing the work. There's nobody operating it, but the computer systems are going through all of the things that this telescope could possibly do and deciding what is the best thing to do next. So if a star explodes, it can immediately start observing it, or it can monitor my star. We then wake up the next day, download the results, analyze them, and do science. So this is a very powerful way of doing science, but it also means we've got an amazing opportunity to get schools involved. And right from the beginning of the project, schools have been part of this. They have time on the telescope. So the project that I run, the National Schools Observatory, is the way in which schools can use the Liverpool Telescope for themselves. And we keep this as broad as possible. We work with, from the youngest, we've got a project running at the moment in nursery schools, right the way through to students doing A-levels. We cover very simple things. This is a group taking a giant picture of the moon and sticking it back together again, and then trying to work out what they're looking at. So then they do the science. But we also get students involved in research. This is a group studying extrasolar planets that have recently been discovered and trying to work out what's going on. And it's not just the science. We talk about the technology and the computing that's essential to get this telescope to work. And because that's very broad, because that really reaches the kind of things that teachers want to do, it's become very popular. JMU support this project, so it's free to anybody. Anybody in the world can sign up and use this system. Most of the resources we have are specifically for UK and Irish schools, though. The website is really busy. We get 3 million people a year visiting it. We've dealt with over 200,000 observations that have gone to the telescope. And we currently have over 20,000 people signed up to use this telescope on a daily basis. This is the very first observation we ever took for a school, about 18 years ago now. And this is not just a picture. This is data that we sent to the school, which we then help them to process to produce that image. So this is their picture. Nobody else had seen this before. This is their own data from a £5 million telescope. We try to cover as much of the universe as we can. So this is an observation, or at least part of an observation, of a small bit of the moon. And if you're in primary schools, it's very interesting to look at this and see where the craters are, and you get these wonderful rays, as we call them, the white lines, which are debris thrown out of the crater at the bottom when an asteroid hit the moon and produced a huge explosion that made the crater in the first place. Now, as a professional astronomer, the moon is basically a nuisance. Because what it is it's big and it's bright and it gets in the way of the stuff I really want to look at. So when I first started working on this project, I spent most of my time trying to work out how we avoided the moon. And then I started talking to teachers and they said, why are you avoiding the moon? We like the moon. And so I started observing it. And we started getting the telescope to observe it, which is really quite difficult with a telescope this big. And I discovered how fascinating it was because it keeps changing. This is a very nice picture of part of the moon. But you wait a week and take another picture of the same bit of the moon, and it's changed. It is exactly the same bit of the moon. If you look closely, you can match up some of the craters. That one up, dark one at the top there, you can match up. And it's different because the light's coming at it from a different angle. And this is an important scientific point. If you just look at something once, you won't understand it. You've got to come back and look again and look at the changes and the differences. So even something that we're as used to as the moon can lead to interesting scientific discussions. But we also get the pretty pictures. There's two here taken for different students that we worked with. The red one there is a star being formed. So the reddish colour there is hydrogen, which is the main ingredient of stars. And the students can measure the size of this. It's very big. You choose a random dot on there that you can see. That's probably about the same size as our entire solar system. So this is an enormous cloud. And in the middle, you have a star forming. But even bigger than that is this wonderful object on the right, a spiral galaxy. And that blue glowing spiral you see there is made up of thousands and thousands of millions of stars, all swirling around in these giant patterns. We live in something like that. And being able to see that and measure it and compare it to other ones means that they can bring the science and make nice images at the same time. Now, it's all very well to do this, but there's no point doing anything unless you're confident that it's doing what you want it to. And so we put a lot of effort into testing what we're doing, making sure that it is achieving what we want it to achieve. And to do that, we have two important things. We have an evaluation framework, which defines how we're going to check whether it's working. And we have this thing on the right, which is our generic learning outcomes. Now, you probably won't be able to read that from where you are, but the important thing is not the details of that, but that it's not just about knowledge. The one at the top is about knowledge. But we've also got skills. Are the children developing technical skills? Can they manipulate things with computers more easily? We've got things about behavior. Do their attitudes to their future change? Are they more likely to choose a different subject area as a result of what we're doing? About feelings. Do they feel more confident about asking questions? Are they satisfied and happy with what they did? And we've got their values. Do they think differently about the role of science in society? Do they think more critically about the role of science in society? These are things that we want the students and the pupils that we work with to develop. And so that's what we want them to do, and the evaluation framework is how we check to see whether it's working. We do lots of other things as well. I won't go through all of these, but we do detailed monitoring of what's happening on the website. We get groups of teachers and students together on a regular basis and talk to them about what we're doing, what we need to change, where it's going to go in the future. But we also get independent people to check. So every few years, we get an external evaluator from another university or another company to come in and do detailed studies of, are we really doing what we think we're doing? So they go and monitor lessons in classrooms. They do interviews with teachers and with pupils. They do large-scale surveys for us. And that's how we know whether or not this is actually working. And the bottom line is, yes, it is. There are things we can improve, but we are helping students to achieve all of those learning outcomes. Their attitudes, their feelings, their skills are all developing. These are some of the quotes we've had from people who've given us feedback during these evaluation reports. One of my favourites is that one from the secondary student. I feel like a proper astronomer. I never felt like a proper anything when I was in school. That's a wonderful thing. But it's the one at the bottom which I think is the most revealing. This was an independent evaluation by a company who spend their entire time going around looking at university engagement activities, university educational activities. And they said that the NSO is one of the most significant initiatives in the STEM field linked to a university. We are doing the right thing. The fact that the university has made this commitment 25 years ago to develop an innovative and imaginative way of engaging with schools is doing the job. So we're very proud of this, and we're very pleased that we're actually being able to make a difference. Because we are, we know we are, we've got the evaluation to prove it. But that's just the UK. What about the world? I'm a big fan of global domination. We do currently work mainly within the UK, and the main reason for that essentially is the amount of time on the telescope. There's only one telescope. It's busy doing lots of research as well. If we start doing this with every country in the world, we're going to run out of time, and people will be frustrated with with the experience. But we're soon going to get an increase in the amount of telescope time, and I'll explain why in a minute. And that will also mean that we can take what we've learnt over the last 15, 20 years and make the whole process even more efficient. So soon, we will be able to expand globally into other countries, supporting their own education systems. But it's not a case of just, here's a telescope, go and play. Every single country in the world has its own education system, its own cultures, its own ways of approaching learning. And we have to adapt to that. So we've started pilot programs. We're doing one in Thailand and one in Kenya, where we're working with educators in those countries, and we're offering what we've got, and they're telling us how we need to change it. And we're learning from that, and we'll soon be able to take that and roll it out to any country in the world. And we'll be able to do that because of this. The Liverpool Telescope has been operating very well for about 18 years. But 18 years is a very long time in science. It's still cutting edge, which is extraordinary. But it's not going to be cutting edge forever. And whenever you're doing anything in science, if you want to stay at the forefront, you've got to plan ahead. And what we're planning to do is build another telescope, a bigger telescope, a faster telescope, a telescope that can do the kind of science that we didn't even know existed 20 years ago. It's going to be working alongside the Liverpool Telescope, so the two of them operating together on La Palma, helping each other, answering some fundamental scientific questions that we haven't been able to cope with before. But we can also do more education. We'll have more time on the Liverpool Telescope, we'll have more time on this telescope, but we can also talk about how you design a telescope, how you build it, how you write the software. We can bring all those aspects of the education in. And so I can honestly say that while our world is becoming increasingly driven by science and technology, we can help people connect with that. If you really want to be a citizen of this world, then you're going to have to be able to engage critically with science. Being trusting of scientists is fine, but unless you understand that trust, there's risks. Astronomy has an incredibly important role to play in that. We can break down the barriers, it can break down the stereotypes. And here in Liverpool, with the Schools Observatory, with the telescope, with all the support we get from JMU, we are leading the way in this, not just in the UK, but around the world. So I've been doing this for over 20 years, but things are just beginning. The next 20 years are going to be even more exciting. So I hope you've got some idea of why I find this interesting, why I find this important, why I get so enthusiastic about it. Before I finish, there's some people I need to thank. In particular, the amazing Schools Observatory team. Ali, Chris, Emma, Jenny and Stacey. As I say, 20 years ago, there were 2 of us on this project, both of us part-time. Now we have 6 of us, again, all part-time. But I can confidently say that these 5 people will take this project over the next 20 years and turn it into something so far beyond what even I imagined that it's going to be extraordinary. So I want to take this opportunity to publicly thank all of those for the amazing work they do and to thank them for all the support that I know they're going to give this project in the future. But I also want to thank the telescope team. They run and operate this telescope. It's not an easy thing to run a robotic telescope, particularly when nobody else has ever done it before. And they do an amazing job of keeping this thing running and supporting all the work we want to do with education. I want to thank everybody in astrophysics. The whole department is always so supportive of all the work we do with schools and with the public. But most of all, I want to thank the university. 25 years ago, they started something which no university had ever thought of doing before, so far ahead of its time. And because of that support, and because that support continues, and because of the enthusiasm we get from all the senior members of the university, we're able to keep doing this, and we will be able to keep doing this for another 20 years. And before I actually finish, and I'm sorry I've gone on a bit long, I just wanted to mention I've written a book. I'm not trying to sell you the book, though. I'm trying to give you the book. At the back on a table, there are some copies of this book. It is the first and possibly only book from LJMU Press. So I wrote this for the university. And if you would like to have a copy of the book, please help yourself. But I would encourage you to make a donation to that website. There's a link to it at the back as well. We're collecting, I'm hoping that you'll donate some money to support the earthquake appeal in Syria and Turkey. So thank you very much for listening. Thank you very much for your attention. But most of all, thank you very much for thinking in your heads about all the things you disagree with me so that you'll come up with some fantastic questions for me. Thank you very much indeed.